Hello and welcome. In this particular video, we're going to be talking a little bit about the harder version of like the reverse chain rule for integration, okay? Previously, before you sort of jumped into this video, you should have had some experience with this rule here. And that's just the reverse chain rule for a very specific case, okay? Just like with integration, remember, right, if we start off with our function there, when we go to our primitive, we add 1 to the power, all right, and divide by the new power. But we also divide by the coefficient of the x term, right? It's almost like we're dividing by the derivative in that particular case, right, of the upper bracket. All right. So what we're going to do is we're going to take the skill and we're going to add a little bit more to it. All right. We're going to go to the more general version. You can just see some of the examples that we went through there in class, but we might talk a little bit more about the chain rule for a general sense. And that is essentially if we have any function that looks like it has a derivative of the function to a power out the front of it, all right, then all we have to do is we just have to take our original function, add 1 to the power, and divide by the new power, okay? So what we're looking for is we're looking for, and this is very, very clearly, it's a specific type of thing, right? Because we're just reversing our chain rule. If you think about the chain rule for derivatives, whenever I do the chain rule, it looks something like this. Y dash is equal to n times f of x to n minus 1 times f dash of x, okay? You'll notice very, very specifically, all right, that we're multiplying by the f dash of x here, all right? And that looks very similar to what we have here, all right? The only thing that's a little bit weird and wacky is the fact that we have an n minus 1 instead of an n and this number at the front. But you're going to see how that all falls out very, very shortly. You'll see how this works out to be the lovely opposite result, okay? But essentially, what we're looking for, the really, really key thing that we're after, is we're looking for a function raised to a power with the derivative of the function out the front, okay? So what I might do is I might get us to jump into sort of having a little bit of a look at this, right? So we can deep dive into it. Here's a basic example. So let's just have a little bit of a look here, okay? You'll notice I have a function and it is to a power. The function isn't linear like before, so we have to be very, very careful. This is where we know that our general rule for the chain rule is going to come in for integration, okay? So let's just have a little bit of a look, all right? Here is my function, all right? F of x is equal to x to the 5 plus 3. And what we're looking for is out the front of this particular bracket here is to have the derivative. Well, let's check what happens when we differentiate just the function on the inside. We're not differentiating the whole bracket. We're just differentiating the function on the inside. Heed my words. So differentiate it. F dash of x is equal to differentiate x to the power of 5 becomes 5x to the power of 4. And differentiate the plus 3, all right, it becomes 0 because the gradient of constant is 0. All right, now let's just have a little bit of a look here. This here is the derivative of the inside of the bracket, and you might notice that we have that here. So we have something in the form of f dash of x times the original function raised to a power. And that fits this exact form up here. So now we can apply the reverse chain rule straight away. All right, doing that, we just simply take whatever it is in here, all right, and we raise that bracket to a new power. So add 1 to the power, so x to the 5 plus 3, all right, to the power of 3. Then we divide by the new power, all right, and because it's an indefinite integral, all right, we just add a constant on, okay? All right, it's as simple as that. That's our most basic example. But the problem is they're not always that simple. So now what we need to do is we need to do a little bit of a deep dive in relation to how some of these examples can get a little bit harder, okay? So let's have a little bit of a look at this example. This is a bit more common of what you would be looking for in these types of examples. So I'm going to tell you my thinking in regards to how to approach this, okay? When I look here, I notice this looks a little bit weird and funky, okay? All right, but what I'm looking for is I'm looking for a function to a power with the derivative of the function out the front. So notice here that I have a function and it's to a power. But I need to check whether the derivative is out the front. So let's check the derivative of the inside of this bracket only. Okay, so what I do, and I encourage you to do this every single time, all right, is I'm going to do f of x is equal to just whatever's inside of the bracket. So x squared plus 1, because that's the function that we're raising to the power. Differentiate it. So f dash of x is equal to 2x. Interesting. So the derivative we need is 2x, but we only have 1x. Well, we can actually fix that, all right? So I'm going to get us to come down a little bit of a line, okay? We need a 2x out the front. Let me just fix that up. We need a 2x out the front for this to be in the form of the derivative times a function to a power, okay? So to do that, I'm going to multiply by 2, okay? Just on that x. The problem is, because I've multiplied by that 2 here, we've actually changed the value of our integral. So how do we fix that? How do we actually change that up? Well, all we need to do is we need to multiply by a half to cancel out the factor of 2. And we're allowed to do that. If I multiply by a half at the front, you'll notice that this 2 and this half will cancel each other out. I might change the color of that pointer. This 2 and that half will cancel each other out. All right. So now let's have a little bit of a look at what's going on here. Okay. I now have the derivative of my function to a power. Okay. The only thing that's changing is that we just need to continue to multiply by this half that's out the front. Okay. So now that we have this form, all right, we've just have to sort of change it a little bit. Now that we have this form, we can actually go ahead and start multiplying. So that half is going to stay there. Oh, let me fix that up. That half is going to stay out the front of the integral, all right? And when we integrate it, we're going to follow the rule for in here. So we take the function inside of the bracket, add 1 to the power, and divide by the new power, okay? All right. And what we're going to do is we're just going to plus c onto the end of it. Why are we plussing c? All right. Well, it's an indefinite integral. Can this c be on the inside of the bracket? It absolutely can. If we put c inside of here, it doesn't matter, because when we go to expand this half, we're still only multiplying by a half by a constant, right? So it's still going to be a constant, whether it's c or k or something like that. It's just a number on the end. Okay, all right. So I'd usually just put the c on the outside of the bracket just for convenience's sake. All right, so plus c. Then do a little bit of tidying up. Okay, I might just come over here. That's equal to x squared plus 1 all to the power of 4 on 8, multiplying the denominators together, plus c. Okay, all right, and that is the integral of x times x squared plus 1 all to the power of 3. Okay. All right. Again, I just really want to highlight it. What we're doing here is, 1, we look for a function to a power with what looks like the derivative out the front. We come over here, we check what the derivative of the function should be. And if this thing out the front doesn't match, we make it match by doing a little bit of manipulation. Okay. So let's have a little bit of a look at the next one. We'll do the next one as well with a very, very similar strategy. All right. Now, what I'm looking for is I'm looking for a function to a power with the derivative out the front. I'll say it one more time. Okay. It doesn't immediately look like that just yet, but let's have a little bit of a look. Okay. So I'm going to rewrite this as x squared times x cubed minus 1 all to the power of a half, because that's what a square root is, dx. Okay. So let's have a little bit of a look. Have I got a function to a power with what looks to be its derivative out the front? Okay, well, you think if I differentiate an x cubed, I'm going to end up with a x squared somewhere. Let's check it anyway. So when I go to check it, okay, all right, we come across, we make this our f of x. So f of x is equal to x cubed minus 1. Let's differentiate it. So f dash of x is equal to, all right, 3x squared when we differentiate x cubed minus 1. So what we need, all right, and I'll put it in red, is we need here a 3 out the front, okay? But if we multiply purely by 3, let me just put it in there. If we multiply purely by 3, all right, we have to cancel it out. we have to also divide by 3. So I divide by a third there. And what happens is this 3 and this 1/3 cancel each other out. All right. All we're doing is we're getting it in that form of f dash of x, all right, of the inside of the bracket multiplied by some function to the power of n. Okay. Now that we've got that, we can add 1 to the power. All right. So we have to keep the 1/3 out there. So we add 1 to the power, x cubed minus 1. Instead of a half, adding 1, we're going to get to the power of 3 on 2. All right. And then we divide by 3 on 2, dividing by that new power, plus c. Okay. So now what we want to do is we want to have a little bit of a play around with what's going on. We can't divide by a fraction, so we're going to flip and multiply it. So this is equal to 1/3 times 2 over 3 x cubed minus 1 to the power of 3 over 2 plus c. All right, doing a little bit of simplifying with these fractions. 1 times 2 will still give me 2. All right, and 3 times 3 will give me 9. So I'm going to end up with 2 out the front of x cubed minus 1 to 3 on 2 all over 9 plus c. And technically we could stop there, but a good habit is because we were given this in rational or third form, okay, we should try and put it back into third form as well. All right, so to do that, it's going to be 2 times. All right, I might get rid of the time sign and just make it a little bit neater. 2 times, it will be the square root of x cubed minus 1 to the power of 3 all over 9 plus c. Okay? All right. So that's how we sort of approach these style of questions, right? We might do one more just to practice what happens when we do it with a definite integral, so you can see what's happening with a slightly harder version. Okay? All right. So let's have a little bit of a look. Right. So this might look a little bit more daunting, okay? But I assure you this just follows the same principle. First things first, we could recognize that this is now a definite integral, which means that we're going to do a numerical answer. I'm not finding the area underneath the curve here. I'm just going to ask you purely just to evaluate it, okay? That just means that I don't want you to worry about whether or not the curve is above or below the x-axis or anything like that. I just want a number answer out of this. Okay, so let's have a look. Does it fit the pattern of a function to a power with the derivative out the front? Well, we have a function and it's to a power. We just need to check whether or not it's got the derivative out the front. Given the fact that this is an x squared, okay, all right, and the thing out the front is a x to the power of 1, it would indicate that it's probably going to look like it's going to be in the form of having the derivative out the front, okay? So it looks like it's going to be a reverse chain rule. So let's have a little bit of a look, right? So we'll come over here to our right, and we'll just look at the original function inside of the bracket. So x squared minus 2x plus 3. Differentiate it, okay? F dash of x is equal to 2x minus 2, all right? Now, what I'm going to do here, you'll notice that this has got an x minus 1 here, and this is a 2x minus 2. It's really horses for courses, depending on how you want to approach it, okay? I'm going to factorize my answer over here, and I'm going to show you why in just a moment so you see what happens. You'll see if I factorize my answer, I have 2x, 2 outside of x minus 1. Why did I factorize my answer? Because it shows me that I have the x minus 1 and the x minus 1, all right? And it then tells me I only need a 2 out the front of it. All right, that makes it a little bit easier for me to work with. So the answer is yes, we have the derivative only if we multiply by 2. All right, so going a little bit further, we'll do the integral from 0 to 1. Okay, we're going to do our x minus 1 outside of x squared minus 2x. I encourage you to do this step each time, please. All right, to the power of dx. Sorry, not to the power of dx. My apologies, writing the dx at the end. And what we needed was to have a 2 out the front for that to be the derivative, okay? Following on from over here. To cancel that out, we must also multiply by a half, okay? All right, so we are on the right track with this particular thing, all right? Now I have it in the form of the derivative, all right? The derivative multiplying the function to a power, okay? So keeping that half out the front, we're now going to evaluate it as a definite integral and put the primitive function inside of our square brackets. Okay, so it becomes the function raised to the new power divide by the new power, and then we're going to evaluate our integral from 0 to 1. Remember, what I can do to make this evaluation a little bit simpler is I can drag this constant of 1/7 out the front, okay? All right, and drag it out of the box. So it's basically going to be me saying, let me just show you again, it's going to be me multiplying 1/7 by 1/2. So out the front of the box, I'm actually going to have 1/14. Okay, and inside of the box, I will now have x squared minus 2x plus 3 all to the power of 7, and we're going from 0 to 1. Do you have to do that? Absolutely not. I purely do that just to make my calculations a little bit easier. Okay, now we're going to apply the FTC. All right, so 1/14, and we're going to multiply that, all right, by subbing in 1 for the furthest away endpoint, squared minus 2 times 1 plus 3, all to the power of 7, all right. Close that bracket off, minus the first endpoint, okay, which is 0 squared, all right, minus 2 times 0 plus 3 to the power of 7. Oops, sorry, let me fix that up. To the power of 7, okay, to the power of 7. Okay, I missed that bracket in the first one, my absolute apologies. Close off and then close again. All right. So we're almost there now, okay? You'll notice that the first set of brackets here is going to evaluate to be 2, and this set of brackets here is going to evaluate to be 3. So we're going to have 1/14 outside of 2 to the 7 minus 3 to the 7. And at this point, you can pretty much just put that in your calculator, all right? And you should end up with the answer of minus 2059/14. Okay, and that is as simple as you can get that answer. So remember the key steps that you're looking for. You're looking for a function to a power with the derivative out the front. And if you don't have the derivative, you do some manipulation. Okay, and then you apply the reverse chain rule. Okay, I hope this has been beneficial for you. Thank you very much.